I think that worked well last time.
The green works pretty good.
You like the green?
Green works okay, yeah.
It's visible.
Okay. So we're going to put two vectors in parentheses and either dot or cross them, and then take either a dot or a cross with a third vector. So again, we'll call our vectors A, B, and C. Now this particular combination, I guess you could call it a double dot product, really doesn't make sense, right? Because A dot B, remember, is a scalar, not a vector. And so the result of dotting A and B together is a scalar. We can't very well dot that with another vector, right? It would have to be a vector to be dotted with another vector. So this combination doesn't make sense. And same thing with A dot B parentheses crossed into C. Because again, A dot B is not a vector, so it can't be crossed into another vector. Right? To be crossed into C, A dot B would have to be a vector, and it's not. So those don't make sense. So the only thing that makes sense would be to cross A and B first. And then the result of that is a vector and can be either dotted or crossed into another vector. So A cross B quantity dotted into C does make sense. So does A cross B crossed into C. And of course, we could have the parentheses in different places, right? We could have the parentheses around the last two, for example, instead of the first two. But these are the kinds of products we want to look at. I'm going to switch to the orange mark because I really think it is better than this green one. So anyway, so let's start out by talking about the triple scalar product. Well, maybe it's not. Try the brown one. The orange one was pretty good on Wednesday. Let's do it. Okay, again, I will get some better markers before this Wednesday. Okay, so the triple scalar product. And that's what this means. Okay, so again, we can put the parentheses anywhere we like. So let's do the cross product after the dot product. Remember that a dot product is commutative. So I could write this quantity here as either A dot quantity B cross C or B cross C quantity dotted into A. Right? The dot product can be either order. Remember the cross product, however, cannot. Right? So anyway, this quantity you can actually show. I'm not going to take the time to do it because I want to move on to get to other topics that I think are more important. But you can show that there are a whole bunch of quantities here that involve these triple scalar products just with the vectors in different orders and different ones getting the dots and the crosses between them. A dot the quantity B cross C is equal to A cross B dotted into C, which is in turn equal to B dotted into C cross A, which is in turn equal to B cross C dotted into A. Can you move that close again? Which is in turn equal to C dotted into A cross B, which is in turn equal to C cross A dotted into B. If you, for example, write out the components, right? We talked about how to do components, how to do cross products and dot products, both in terms of components last time. So if you write out the components of, for example, B cross C, and the components of A and do the dot product between them using our component-wise way of doing dot products. And the same for all these other combinations. You can show that these are all equal. It's a lot of algebra, and so I don't want to take the time to do it. Okay, but these are all equal to each other, and I know this looks like kind of just a jumble of letters here. But the way to remember this is notice, and in fact you can relate this to this thing about cyclic and anti-cyclic permutations that we talked about last time. Let's take the three vectors A, B, and C and write them around a circle going clockwise in order A, B, C like this. And the point is that in writing these combinations, I can start at any point I want around the circle. I just have to go clockwise and write the vectors in the order they appear. So I can write A, B, C in that order, A, B, C here also, or I can start at B and do B, C, A, B, C, A right there, B, C, A right there, or I can start at C and do C, A, B, C, A, B, C, A, B, okay? And then I can put, when I have those three vectors written in that order, I can put the dots and the crosses between them anywhere I want, as long as I have two of them with a cross product in parentheses, because again, I have to cross two of them first to get a vector, which can then be dotted with the other vector. So I can put a dot in one place and a cross in one place as long as I put parentheses around the two vectors that are crossed together then. So, in other words, I can write them in any cyclic permutation of the letters A, B, C. That's, remember what this means. I can start at any of three I want to. Just go around clockwise to get to the other two and put write all three of them down in that order. And then again, I can put the dots and crosses, a dot and a cross wherever I want, as long as I put the parentheses around the cross product. So these are all equal to each other. I'm just going to call these X for a moment, just so I don't have to keep writing such a long expression. And then you can also show that if you write them in an anti-cyclic order, in other words, an order, again, I can start with any of the three I want, but now instead of going clockwise, I'm going to go counterclockwise around the circle to get to the other two. So I start at A, I'll write A, C, B. And again, I can put a dot one place and a cross the other place. For example, a dot there and a cross there. And then put parentheses around the cross product. This is equal to, again, I'll write them in the same order, A, C, B. But now, instead of the dot here and the cross here, I'll put the cross here and the dot here. Again, I put parentheses around the cross product. Those are equal. But also I could start at B, and again, instead of going clockwise, I'm now going to go counterclockwise. So B, A, C. And again, I could put the dot and the cross wherever I want. Just put parentheses around the cross. Or I could start at the C, and again I'm going counterclockwise, so that would be CBA. Again, I could put the dot and the cross wherever I want. Just put parentheses around the cross product. So if all these first six that were equal to each other were called X, then these next six expressions that are all equal to each other are minus X. Right? These six are the negative of what those six are. Right? So again, if you write out components of all those expressions, you can show that. I'm not going to take the time to do it. But in terms of components, a triple scalar product, let's look at this one. A dotted into the quantity B cross C. This can be written as the determinant of a matrix, which is maybe not surprising since we found last time that an ordinary cross product can also be written as a determinant of a matrix. Remember, if we were just crossing B and C together, remember how we would do it as a determinant. We would write the unit vectors I hat, j hat, and k hat along the first row. We would write the components of B, bx, by, and bz along the second row, and the components of C, the second vector, and the cross product along the third row. Alright, so again, if I were just crossing B and C, I'd have this determinant, but I have an I hat, j hat, and k hat here. But now, if I take that and I dot it into A, remember that A dot D would be AX dx plus AY dy plus AZ dz. So I think if I think of D as representing B cross C, I'm dotting right, A into D, and that means I multiply, again, the x component of A times the x component of D, and so forth. Well, the x component of D, or B cross C, would be the coefficient of the I hat that goes up here. When I dot that into A, essentially it means I'm taking the determinant of this matrix. Oops, I'm sorry, that should be AZ. And so the one that's dotted into the others goes go across the top row, and then the two that are crossed into each other go across the second and third rows. Of course, the first one here and the cross product goes in the second row. The last one goes in the last row. Okay, so in terms of components, that's how you can find a triple scalar product. And we already looked at an example of a triple scalar product actually last time. Just before the end of class, our last example, we looked at the torque produced by, let's say, somebody pushing with a force on a doorknob to open a door, for example. We talked about the torque along the hinge line, or the axis that the door rotates around. And that was an example of a triple scalar product, because first of all, we found a torque by doing R cross F, right? And a position vector crossed into a force vector. R in that case was a vector pointing from the origin to the place the force was applied. That gave us the torque about that origin. But then if we wanted to find the torque around a particular line, like that hinge axis of the door, we took the R cross F torque and we dotted it into a vector called n hat, which was a unit vector along the axis. Okay? So again, we've already actually seen an example of this. Okay, so let's take a little, I want to see if these markers that are here in the room are any better than the ones I have with me. So we looked at this one, right, the triple scalar product. Don't look too good either. So let's take a look at this one, the triple vector product. That one's going to be bright enough to really see. I'm going to just call somebody and ask them to bring up a few more markers, okay? So I'll try again in a few minutes. Meanwhile, we'll keep going with the brown one. I think that's the best we've got here. Okay, so let's look at the triple vector product. So this is something like A crossed into B cross C. Right? So both products are cross products in this case. And again, B cross C is a vector, so it can be crossed into another vector A without a problem. Well, remember that when we do the first product, first cross product, B cross C. This is perpendicular to B and also perpendicular to C. Right? Cross product of two vectors is perpendicular to both of the vectors that you cross together. And then that also means that A crossed into B cross C, parentheses, must similarly be perpendicular to A and also perpendicular to B cross C. Okay, I'll try once more, and if she's not back, I'll run down and get some myself. Anyway, so since A cross the quantity B cross C is perpendicular to B cross C, right, that was one of the statements we just made. And B cross C is in turn perpendicular to both B and C. This means that A cross the quantity B cross C must be in the plane containing B and C. Right? Because here's our reasoning. Right? A cross B cross C was perpendicular to B cross C, but B cross C in turn was perpendicular to both B and C individually, and therefore, if B and C, think of there being a plane that has both the vectors B and C in it. B cross C is then perpendicular to that plane. Okay? But then perpendicular to B cross C must be this triple product, therefore it must be in that same plane that B and C were both originally in. Okay? And so that means that therefore we can write the quantity A cross B cross C, this triple vector product. We can write it as some kind of coefficient, let me call it alpha, a scalar coefficient times B, plus another scalar, let me call it the Greek letter beta, times C. Right? In other words, A cross B cross C is a linear combination of B and C. It's equal to some scalar coefficient times B plus another scalar coefficient times C. I call those scalar coefficients alpha and beta. The only remaining problem is to find out what alpha and beta are equal to. Okay, so anyway, you can show, and again, I'm not going to take the time to do this because it involves a lot of algebra where we write down components of all these things. And I'd rather spend that time doing other things that I think are going to be more important for us. But you can show that alpha, the coefficient of the B vector here, is A dot C. Of course, A dot C is a scalar, not a vector, right? So that's a perfectly okay thing for alpha to be. And that beta, the coefficient of the C vector, is equal to minus A dot B. So, in other words, A crossed into the quantity B cross C is equal to A dot C quantity times B. Again, A dot C is a scalar, so it can multiply a B without there being a dot or a cross in between here.
Is that a minus A?
Right here? Yeah. And so you can see that here in that next term, this will be then minus the quantity A dot B times C. Okay? So again, A dot B is a scalar, so it's a perfectly good coefficient for this vector C without, we don't need a dot or a cross in between it. Anyway, this rule right here is something called the back cab rule. And I guess the way to remember it, it doesn't quite look that way the way I wrote it down. But in this first term, we could have written the A dot C after the B, right? It doesn't matter whether it's before or after, right? 2 times B is the same as B times 2, right? 2 is a scalar. So instead of 2, it's A dot C here. That's a scalar. That can go either before or after the vector B. And so if you wrote it after instead, the order here of the 3 vectors would be B, A, C. And if you similarly here wrote the C before the A dot B, it would be C, A, B would be the order of the vectors there. And so that's the way that they are listed in this kind of mnemonic for this rule. Yeah?
So the B and the C is just regular multiplication, just vector multiplication?
What do you mean?
Scalar multiplication, I think is what
You mean the A dot C times B? That's ordinary multiplication, because that's just a scalar multiplied by a vector, right? Because A dot C is a scalar, not a vector. So it doesn't need to be dotted or crossed into the B. It can just be multiplied, right? Because the scalar can just multiply by a vector. Let me make one more attempt here to get some more of these pens brought up. I'm going to go and try to find some pens myself. Nobody's down there in the office, so I will be right back.
I'll leave you guys in the Oh, really?
Share this with
It'll go up on YouTube.
Huh?
It'll go up on YouTube. I'll post the link on the class Blackboard.
Cool.
Originally have in the triple cross product are not A, B, and C, right? Or maybe they are A, B, and C, but in some different order. So it would be helpful if there were a mnemonic to remember this, and there is. Okay. This one is a little bit. These are supposedly fresh ones. So the result of a triple vector product, and what I'm about to tell you will be true whether the vectors are called A, B, and C or something else, whether the 2 in parentheses are the first and the second ones or the second and the third ones, doesn't matter, okay? I'll tell you a way of remembering how to use this back cab rule no matter what kind of triple scalar product you're starting, or triple vector product you're starting with. So the result is a linear combination of the two vectors in parentheses. So in our case, that's the B and the C, right? So there's a B, there's a C. Each one of them gets multiplied by a scalar coefficient, right? And so the scalar coefficient of each of those two vectors, so the scalar coefficient of each is the dot product of the other two vectors. Right, so the term that has the B in it, the coefficient of the B is A dot C. The term of the C has an A dot B as a coefficient. And so there are two such terms, right? One for each of the two vectors in parentheses originally. One of those has a plus sign in front of it, one has a minus sign in front of it. The one that has as a vector, not the scalar coefficient, but the vector B, right? Not B as part of the scalar coefficient, part of the dot product, in other words. That is the middle one there in the original vector product, and that's the one that gets the plus sign, okay? So there will be a plus sign in front of the vector that was originally in the middle between the other two, in the original vector product, and a minus sign on the other term. Okay, so in other words, if I had, let's look at maybe R cross F cross A. Okay? These could be any vectors you like. R cross F maybe it looks like it's a torque. I don't know what A is. Let's just say you're trying to analyze some kind of vector product like this. So according to the rule that we just said, this would be a linear combination of the two vectors in parentheses, namely R and F. So something times R, either plus or minus, we'll fill in the sign in a moment, something times F, right? And the coefficient, the thing that goes in parentheses in front of each of those vectors, is a dot product of the other two. So this one has R up here, so it'll be an F dot A or an A dot F. Of course, we could write that either way because remember, a dot product is commutative. And similarly, this term where we have an F there, there'll be an R dot A or an A dot R in the parentheses in front of it. And whichever term involves the vector in the middle of the original cross product, that's the F. Okay, so this is the term that has a coefficient times F. That term has a plus sign on it. The other term then has a minus sign. Okay? So that would be an application of the back cab rule where the vectors aren't called A, B, and C, but this little mnemonic here will still help you remember how to write that. Okay, so your book does a lot more than this with triple scalar products and triple vector products. They talk a little bit about geometrical interpretations and things like that. Again, I don't want to waste time doing, or maybe I shouldn't say waste, but I don't want to spend time doing that because we have other topics to get to that I think are more important and that we need to spend more time on. But I just wanted to mention these. There is a table of vector identities, I think, in the front cover of your book, or maybe in the back cover instead. And they are things you're occasionally going to have to use when you're working a problem. And so the back cab rule that I just showed you right there is one of them, and I think this one right here is listed as another one of them. So just be aware you can use those things if you need them. I'd like to move on to doing calculus with vectors. Right? That's sort of the point of really the vector calculus, obviously since it's called that we're doing in this course. So everything up until now is just really an introduction to the vector calculus. So let's consider a vector, we'll call it A. That is a function of some scalar. Right, and let's call that scalar t. And that maybe suggests time, so we certainly could be looking at a vector that is a function of time. But again, I'm trying to just, keep it pretty general mathematically at this point. So it doesn't have to be time, but certainly in many physical examples it will be. So first of all, what do we mean by a vector being a function of a scalar? Well, A, like any vector, could be written in terms of components. A sub x times I hat plus A sub y times j hat plus A sub z times k hat. But this means the components are each functions of time. So A sub x is a function of time, A sub y is a function of time, and A sub z is a function of time. Okay. So each of the three components are a function of t, whether that's time or some other variable. Doesn't matter. Okay, so anyway, then the derivative of A with respect to t and of course we write that as dA dt just like we do for an ordinary derivative. And just like an ordinary derivative, what this really means is a limit of the vector A evaluated at t plus delta t minus A evaluated at just t divided by delta t, and we take the limit of this as delta t goes to 0. Right? So again, just like an ordinary derivative, right, the derivative of f of x with respect to x is f of x plus delta x minus f of x divided by delta x. Take the limit as delta x goes to 0. Same idea here. So think about an example, right? Graphically. Let's say at time t, the vector A is represented by this little arrow right here. And then maybe at some later time, t plus delta t, now A is a new vector represented by this arrow right here. Perhaps, for example, this is the position vector of some object. Right? And relative to an origin right here, at time t our object's located here, at time t plus delta t is located right there. So the numerator here, which is sometimes of course also called delta A, that's going to be a vector that points from the tip of A of t to the tip of A of delta t. So this vector here is delta A, or in other words, A of t plus delta t minus A of t. You can see that vector addition, the graphical way of doing vector addition works here. Right? I could find A of t plus delta t by taking A of t plus delta A. That's just a rearrangement of this equation here. And so if I draw A of t, and then I draw delta A with its tail starting at the tip of the tail of the A of t vector, and add those together, gives me a result A of t plus delta t that starts at the tail of the first one and goes to the tail of the second one. Right? So graphical vector addition works here. So anyway, in terms of components though, right, it's usually most convenient to work in terms of components. When we have a vector A of t written in terms of components, a sub x times I hat plus a sub y times j hat plus a sub z times k hat, like this, the derivative of a with respect to t will then be the derivative of a sub x with respect to t times I hat plus the derivative of a sub y with respect to t times j hat plus the derivative of a sub z with respect to t times k hat. Right? This is exactly what you would expect if you take the vector A written in terms of components like this, and you take the derivative of that with respect to time, it will give you that expression over there. But keep in mind, we are kind of sweeping one thing under the rug when we do this, which is okay in this case, but will come back to haunt us later when we look at other coordinates besides Cartesian coordinates. Of course, we're using Cartesian coordinates here, right? Because we've got I hat, j hat, and k hat unit vectors. That means we have x, y, and z axes. When we take the derivative of this expression here with respect to t, or time, we are assuming I hat, j hat, and k hat themselves are not functions of time. Okay? Then that will give us this expression here. But if I hat, j hat, and k hat themselves depended on time, when we took the derivative with respect to time, for example, of this first term here, we'd have to use a product rule, and we'd have two terms. We'd have a derivative of a sub x with respect to t times I hat. In other words, the first term we have right here. But we'd also have an a sub x times the derivative of I hat with respect to t. Okay? That term we can leave out because I hat doesn't depend on t. Right? Direction of the x-axis, which is the direction of the I hat unit vector, does not change with time. Right? It's always pointing in the same direction. And certainly the magnitude of that I hat unit vector doesn't change with time. It's always 1 because it's a unit vector. So in other words, I hat doesn't depend on t, and that's why we didn't need that extra term, and of course the analogous two terms would come from differentiating these two terms also. So that's why we only have 3 terms, not 6 terms here. But if we had unit vectors that were functions of times, we'd have some additional terms. It turns out in other coordinate systems, which we're going to get to later, that will happen. And we'll have to worry about that. Okay? So we'll deal with that when we get there, but just a reminder that we are here using our knowledge that I hat, j hat, and k hat do not depend on t. Okay, so this is what we mean by the derivative of a vector with respect to a scalar. So, of course, some obvious examples of this. If the position of an object changes with time, so the position of that object, let's call it r. So in other words, r is a function of t. So it has, r has, not right on, but I'll just write it like this. Right? An r vector, a position vector, has components x, y, and z. So each of those gets multiplied by the appropriate unit vector. But now, since r is a function of time, x, y, and z are each functions of time as well. Okay? Then the velocity of the object, v as a function of t, is the derivative of r with respect to t. So in other words, this is dx dt times I hat plus dy dt times j hat plus dz dt times k hat. In other words, v sub x, the x component of the velocity, is just the derivative of x with respect to t. Similarly, v sub y is dy dt, and v sub z is dz dt. And in fact, we could then take one more derivative with respect to time to get the acceleration. So the acceleration, which can also be a function of time, right, that will be the derivative of v with respect to t, or in other words, the second derivative of r with respect to t. So just differentiating this one more time, that's the second derivative of x with respect to t times I hat, plus the second derivative of y with respect to t times j hat, plus the second derivative of z with respect to t times k hat. There are also a list of rules here that come into play when we're taking derivatives. If we have the derivative of the quantity little a times capital A, where little a is a scalar, right? And little a could depend on time also, right? A scalar could be a function of time also. So basically we're talking about a product rule type thing. This works exactly how you think it would be. You'll have one term where the derivative operates on the little a and the big A just comes along for the ride, plus another term where the little a just comes along for the ride and the derivative operates on the big A. We can also think about a dot product of, for example, a time derivative, or derivative with respect to t. Again, t may not necessarily be time. A derivative of a dot product, right? Maybe the vectors a and b both depend on t, so their dot product, again, this is going to be a product rule sort of type thing, and it works exactly the way you would expect. You'll have one term where the a comes along for the ride and the derivative operates on the b, and you have another term where the a comes along for the, the derivative operates on the a and the b comes along for the ride. Of course, since there was a dot product in the original one, there's a dot product between the a and the b in each of those terms, right? Just one has a derivative operating on it and one doesn't. Of course, a dot product is commutative, by the way, so either of these terms, right, for an example, in this term, the v, I could have written this term as v dotted dA dt. And the dot product is commutative, so I could write it in either order. There's a similar product rule for a cross product also. Again, if a and b are both functions of t, if I want to differentiate the cross product of a and b with respect to time, this is, again, a cross into dB dt plus a cross, I'm about to write the same term over again, plus dA dt crossed into b. Now, on this expression, you have to be careful not to change the order of the cross product in each term. A cross products we know are not commutative. A cross B is not the same as B cross A. And since the original cross product had A first and then B, in both of these terms you have to have A first and then B, right? Regardless of which term has the time derivative on it. Okay, so anyway, what I'm sort of suggesting, and maybe I should have said this when we started out this discussion, but when we think about a vector as a function of a scalar, like t, like I wrote over there, right? Again, perhaps the implication was that t was time, but it doesn't necessarily have to be. The mathematical statements I made would apply to any scalar t. So we could also have a scalar that depends on position. So for example, we could write, I'm going to use phi, the Greek letter phi for the scalar. That's a symbol we often use for angles, but I'm not necessarily talking about an angle right now. Okay? Talking about some scalar that depends, let's say, on our three-dimensional coordinates, our three-dimensional Cartesian coordinates, x, y, and z. So in other words, what I'm really describing here is something called a scalar field. That's the technical name for this. Okay? In other words, there is a scalar sitting at each point in space. Okay? So at each point in space, at each location, which is given, of course, by a unique set of coordinates x, y, z describing that location, there is a scalar, or just a number, sitting at that point in space. Okay? Some examples of what I could be talking about by using a scalar field like this would be, for example, the temperature in a room. Right? Maybe it's a different temperature in different parts of this room than others. And so imagine at each point in the room, each position x, y, z, there's a number sitting at that location telling you what the temperature of the air at that location is. Okay, so it might be higher in some places, lower than other places, or it could be uniform, could be the same everywhere in the room. Okay, you could imagine also something like the price of houses in an area. Right, at each location in an area where there's a house, there is a number sitting at that location that tells you the price of that house. Right? And so it's some function that changes as a function of position. So those are examples of scalar fields. You can also have a vector field. Okay? In other words, a vector sitting at each point in space. So you could, for example, have a vector field V, function of x, y, and z. Again, what this really means is that V, like any vector, can be written in terms of components. V sub x times I hat times V sub y times j hat plus V sub z times k hat. But V sub x is a function of x, y, and z. And similarly, V sub y is a function of x, y, and z. And V sub z is a function of x, y, and z. Notice that any of these three components can depend on all three coordinates. In other words, V sub x is not only a function of x, and V sub y only a function of y, and V sub z only a function of z. Each one can depend on all three coordinates. Okay? Okay, so that's a vector field, and there are lots of physical examples of that you can imagine also. The velocity of water in a river, for example. At each location, x, y, and z, inside the water in the river, there is a vector sitting at that location telling you what the velocity of the water at that point is. And of course, velocity is a vector, has both speed, in other words, magnitude, and direction. Right? So at each point, there is a vector sitting there that tells you how fast the water at that point is moving and in what direction it's moving. that could be uniform. In other words, you could have a nice smooth flow where the velocity was the same everywhere in the river, but you could also have a velocity that varies from point to point, from location to location in the river. Right? And maybe it's moving faster some places than others. Or maybe the direction in which it's moving is different some places than others. Maybe there's a little whirlpool at one location or something like that. Right? So there could be all sorts of things in that vector field that describe perhaps a very complicated motion of the water in the river. Another example, of course, would be an electric field. Right? An electric field is a vector. It can vary from point to point in space. Right? So again, it points in a certain direction, so it has x, y, and z components. Each of those could be functions of position. Right? A magnetic field would be another example. So there are all sorts of vector fields that we have to deal with in physics. And so we're going to be doing, in fact, there are scalar fields we have to deal with too. So both for vector fields and scalar fields, there are various kinds of derivative-like operators that we need to talk about. Things that are sort of like derivatives. Except, when we were talking about derivatives here, we were only looking at a vector that was a function of one variable, namely t. Now we've got a vector that is a function of three variables, x, y, and z. So, of course, things can get more complicated. So let's start out by looking at a scalar field. Okay, so think about a scalar field. Again, we'll call it phi. It is a function of x, y, and z, or perhaps for short, we could just say it is a function of r, because r is the vector whose components are x, y, and z. Okay? So that scalar field has a particular numerical value at a particular point x, y, and z, particular choices of the coordinates x, y, and z. So let's then move to a new position, only infinitesimally far from our old position, x, y, z. So our new position will have coordinates x plus dx, y plus dy, and z plus dz. Or in other words, we could say that our new position is r plus dr. Right? Our original r had coordinates x, y, z. We add an amount dr and an infinitesimal displacement vector. Dr has coordinates dx, dy, and dz. So our new position has these coordinates right here. Right? So the change in our scalar field or in other words, the total differential of our scalar field right? These are two expressions for the same thing. In other words, d phi, right? The amount by which phi changes. Well, since phi is a function of three variables, x, y, and z, we can write this as a partial derivative of phi with respect to x times the change in x, or dx, plus the partial derivative of phi with respect to y times dy, plus the partial derivative of phi with respect to z times dz. Well, let's define a quantity that's closely related to this. Let's define the gradient of this scalar field phi. We use this symbol for it, right? It's an upside down triangle with an arrow over it telling us this is a vector. We read that as del, okay? So we call this del phi, or the gradient of phi. this is by definition the partial derivative of phi with respect to x times I hat, the unit vector in the x direction, plus the partial derivative of phi with respect to y times j hat, plus the partial derivative of phi with respect to z times k hat. Did I tell you I was going to use I hat, j hat, k hat, or x hat, y hat, z hat?
Twice.
Yeah, just remembering I did that. So let me try to switch here. Okay, your book, remember, uses I hat, j hat, and k hat, but I prefer this notation. So anyway, this is the gradient, right? This is what we mean by the gradient of this quantity phi. Now notice that phi was a scalar field, but when we take the gradient of it, our result is a vector field. Right? Our result is clearly a vector because it's got unit vectors, x hat, y hat, z hat in it. And then the coefficients of each of them, well, these things could be functions of x, y, and z also. Right? Phi is some function of x, y, and z, and there's no guarantee that when I take these partial derivatives, I'm going to get constants. They could still be functions of x, y, and z. So this gradient gives me a vector field, right? Something with a direction. It's got unit vectors in it, making it a vector, and the components could be functions of x, y, and z. So the result is a vector field. Then this quantity d phi, the total differential that I wrote right here, I could write as the gradient of phi dotted into dr vector, right? Because the gradient of phi, again, if I write out the definition of that right here, and I'm going to dot that into dr, which has components, right? It can be written in terms of components as dx times x hat plus dy times y hat plus dz times z hat. And then, of course, when I take the dot product of two vectors, I multiply the x component of one times the x component of the other. So that gives me the partial of phi with respect to x times dx, plus the y component of this one times the y component of that one, plus the z component of this one times the z component of that one. And, of course, that agrees with the d phi I wrote right here. Right? So you can see with this definition of the gradient, the way I have it, that then this total differential can be written like that. Before we go on, let's maybe talk a little bit about the intuitive meaning of a gradient. Right? What are we finding intuitively when we find the gradient of a scalar field? Well, perhaps the most familiar example is displayed as something you might have encountered as a contour map. You could think of the elevation above sea level as a function of x and y, which are two-dimensional coordinates of the surface of the Earth. In fact, perhaps you want to think of it as, if you wanted to draw x and y axes, perhaps you wanted to think of it like on a map, where maybe the y direction is north, the x direction is east, the minus x direction is south, and the minus y direction is west. Right? And you're looking down on a landscape then as seen from above, somewhere up in the air, And you might see on a contour map showing that region, you might see things like this, and perhaps each of these contour lines is going to be labeled with a number that shows you the elevation at that point. And so you're thinking of the elevation, now when you're thinking about the elevation as a function of y, we're of course thinking about a scalar field that depends on only 2 variables, not 3 variables. In a sense, if you want to think of space as 3-dimensional, instead of treating perhaps the z direction, which might be out of the board here in this picture, I'm thinking of z as a function of x and y, or if you prefer, call it the height above sea level, or the elevation as a function of x and y. So that could be a scalar field, right? Instead of phi, I'm calling it z or h or whatever. And again, it depends on only 2 variables in this case, not just 3. So at each point on the plane here, on the surface of the Earth, imagine there's a number at that location that tells you the elevation at that point. And the contour map is a way of indicating that. Basically, all the points that are connected by the same curve, for example, at this point right here and this point right here, right? The elevation is the same at both of them. So you connect all points that have the same elevation by a line or a curve. And again, you can put a number on each curve with showing you what the actual elevation is at that point. So something like this could designate a mountain. Maybe it's a peak kind of right here or something. Or, right, that would be if the numbers got bigger as you went in. If they went smaller as you went in, of course, it could represent a valley instead of a mountain. So that would certainly be an example of something that could be represented by a scalar field like this. So on a map like this, on a contour map like this, let's think about the meaning of what the gradient is. We haven't tied the gradient into this yet. So let's consider a displacement. We're at some particular location, x, y, right, on that contour map, like a dot like right here. Right? And let's consider a displacement, a vector dr, an infinitesimal displacement that is tangent to a contour line. Okay, so if I'm at this location right here, consider a dr like that, okay, tangent to this contour line that I'm on. So imagine moving a little bit in that direction. Well, the change in phi, if I move along a contour line, is going to be 0, right? Because phi, by definition, is constant, or z or h or whatever it is. Let's call it, since I've already used it, think of this as phi of x and y, to again be consistent with the notation we used over here. So phi doesn't change if we move along a contour line, right? And so the infinitesimal change in phi when I move in this direction along a contour line or tangent to a contour line by an infinitesimal amount, phi isn't going to change. So d phi has to be equal to 0. Well, we already said over here that d phi was equal to the gradient of phi dotted into dr. And we certainly know, so in other words, this is going to be 0. Well, we know dr isn't 0 because we know we've moved some infinitesimal amount. And we certainly shouldn't assume in general that the gradient of phi is always going to be 0 either. So how's the other way that we can make this dot product 0? Well, we know that the dot product of two vectors is going to be 0 if those vectors are perpendicular to each other. Right? So this means if d phi here is going to be 0, that means this dot product is 0. So that means the gradient of phi is going to be perpendicular to the displacement that we moved along when we did this. And we moved along a displacement dr that was tangent to the contour lines. So that means that the gradient of phi must be perpendicular to the contour lines. Okay, so if we're at this location, to move perpendicular to our contour lines, we either have to be moving that way or that way, right? Either kind of to the right or kind of to the left, perpendicular to the contour lines. That's one or the other of those has to be the direction of the gradient of phi, according to what I just said right here. So the only question is then in which of those two directions it's going to be. So we're going to define the gradient of phi to be perpendicular to the contour lines in the direction in which phi is increasing. In fact, it turns out that if we're at any location on our contour map, that the direction of the gradient of phi is in the direction where phi increases most steeply. So in other words, if this is, again, a contour map showing the actual elevation at some two-dimensional coordinate x, y, then if I'm at this location right here, and these are my contours, in other words, my lines of constant phi, and let's say that, phi is maybe equal to 5 along this line, 10 along that line, 15 along the innermost contour line in whatever units I've measured those in. Then if I'm located right here, right, if these are elevations, that means that's going to be describing a mountain, not a valley. So the direction of phi would be the direction that when I'm standing here is in the steepest uphill direction. Okay? So along the lines will be places that are at the same elevation I'm at, and if I turn around and look at all directions, the direction which I'm looking uphill most steeply, that's the direction of the gradient of phi at this location. Okay? So again, this is a vector field, right? It could be different vectors at different points in space. If I'm right here, the direction in which the terrain goes steepest in the uphill direction from where I'm located is that way. Okay? So this is the direction of the gradient of phi. But if I'm over here, for example, the steepest uphill direction will be that direction, right? So again, the gradient will point in different directions at different points in space, different locations. Okay? So it will point in the direction that is steepest uphill. So let's look at an example of a function where we actually calculate its gradient and make a map, sort of like the ones we were referring to. The advantage of a scalar field that's a function of two variables rather than three is that we can draw contour maps like what we were talking about there for a scalar field that's a function of two variables, but we can't really draw something on a two-dimensional blackboard for a three-dimensional vector field. So let's look at a two-dimensional example. let's say we have a scalar field phi that is equal to x times y. Right? So the contour lines, if I want to draw a contour map of this, in other words, for phi to be a constant, means that the product of x times y is a constant, which, if I solve for y as a function of x, means that y would be equal to that constant divided by x. So if I want to draw a sketch here are my x and y axes, sketching some contour lines, I would use a different value of this constant for each line and simply label each line by the value of that constant. Okay? So for example, if the constant was equal to 1, I would be drawing a graph of y equals 1 over x, which looks something like this. So I'm going to label that with 1, and in fact I can draw another piece of it over here. Right? If x is negative, y is negative also. Right? So that's a graph of the curve y equals 1 over x. I could use a different constant. What if the constant is 2? I could draw a graph of y equals 2 over x. That looks maybe something like this. And another piece down here. There's no rule that the constant necessarily has to be a positive number. What if the constant were equal to minus 1? Right? Then I'd be drawing a graph of y equals minus 1 over x. That would have a branch like this over here, and like this over here. If the constant were equal to minus 2, and I draw y equals minus 2 over x, that would have a piece like that and a piece like this. I could also have the constant be 0. Right? If the constant were 0, then y would be equal to 0 no matter what x is. And so, of course, y equals 0 is the x-axis. So right along the x-axis, I'd have a curve that I could label with the value of 0. Okay, so those would be some contour curves for this particular function. Let's calculate the gradient of this function. So the gradient of phi is the partial derivative of phi with respect to x times x hat, plus the partial of phi with respect to y times y hat. Of course, this is only a 2-dimensional example, so I just leave off that third term, right? Phi doesn't depend on z, or in other words, that third term, where's my definition over here? This third term is 0. So if phi is this expression right here, the derivative of phi with respect to x just gives us y. So this is y times x hat, plus the derivative of phi with respect to y is just x. So x times y hat. So the gradient of phi is x times, or is y times x hat plus x times y hat. So for example, let's look at the point 1, 1. Right? X equals 1, y equals 1. Notice that x equals 1, y equals 1 means that phi equals 1, or in other words, the constant here is 1. So that's a point along this curve right here that I've labeled on the number with the number 1, and it's right there. And it's 1 unit over and 1 unit up. So at that point, let's evaluate the gradient of phi. So here's the gradient, so we just plug in x equals 1, y equals 1, and the gradient of phi is then x hat plus y hat. So let's, at that point, imagine what direction that vector is in. And so at this point, a vector that points 1 unit to the right and 1 unit up is a vector pointing in this direction. So that's the direction of the gradient of phi, and you can indeed see that, and if you were standing on a surface that had contour elevations, like the ones we have labeled here, right? This would be a higher elevation than that, this would be lower. So if you were standing here, that direction would be the steepest uphill direction, exactly what we've said. Let's look at another point, right? Just to convince you it's always going to be the steepest uphill direction. Let's look at the point 1 minus 1. So that's 1 unit over and 1 unit down, and it's right here along this curve because x times y is minus 1. In other words, phi is the value minus 1, or this constant is minus 1 at that position. So, so we're along that curve. So anyway, at that point, the gradient of phi, it's again, in general, y times x hat plus x times y hat, but now y is equal to minus 1, minus x hat, x is equal to plus 1, so minus x hat plus y hat. So from that location, we could draw a vector that points to the left 1 unit, because it's a minus x hat, and up 1 unit, because it's a positive y hat. So this would be the direction of the gradient of phi at that point. And again, that's in the direction pointing steepest uphill. We're on the line marked with an elevation of minus 1. Remember, the x-axis is the elevation phi equals 0. So this is a higher elevation than this, and this is pointing in the uphill direction at that point.
Sorry, so if our x-coordinate is minus 1, wouldn't it be on the other side?
Our x-coordinate is plus 1,
Oh, okay.
our y-coordinate is minus 1.
So the unit vector then is pointing in the direction of the negative x and the positive y?
The gradient.
The gradient, yeah.
Yeah, because the gradient came from this, and into this expression I plugged y equals minus 1 and x equals plus 1.
Okay.
Okay? Okay, there's something very closely related to the gradient called the directional derivative. Okay, so what we mean by the directional derivative is the change in the scalar field phi when we move along the direction of a unit vector. We'll call it u hat. Right? Anytime we see a vector with a hat over it, it tells us it's a unit vector. This can be in some arbitrary direction. But we're going to move along that direction as defined by that unit vector by an infinitesimal lemma we'll call ds. Okay, so the directional derivative, which we'll often write as d phi ds, is the gradient of phi dotted into the unit vector whose direction we want to move along. This comes from this right here, right? We said that if we move along a vector dr, that the change in the scalar field phi as we move that infinitesimal distance along it is given by the gradient of phi dotted into dr. So all we're going to do here is set dr equal to ds times u hat. Okay? So in other words, dr we're going to say has a magnitude ds. That's the distance we move. Right? And it's the direction defined by the unit vector u hat. So if we do that, we can write d phi as the gradient of phi dotted into ds times u hat. Well, the ds is a scalar. It can be brought out in front. So we just have the gradient of phi dotted into u hat. I'll put parentheses around that. And now you can imagine just sort of dividing by this infinitesimal distance ds that we move. And that gives us an expression for d phi divided by ds, or in other words, this directional derivative, as the gradient of phi dotted into a unit vector along the direction we want to move. Okay? So let's think about what this means as maybe applies to that previous example over here. Okay? So in that example that I have over there on the right-hand board, let's say we start at the position 1, 1, right? X equals 1, y equals 1. And we want to move in the minus y direction from that location. So according to the notation that we used here, where it said we're going to move in the direction of a unit vector u hat, so if we're moving in the minus y direction, then our u hat is minus y hat. Okay? So the directional derivative, d phi ds, when we move in that direction, our general expression here for it, we said, is the gradient of phi dotted into u hat. Well, we already found for this example the gradient of phi right here is yx hat plus xy hat. We're going to dot that into our u hat, which is now minus y hat. So, of course, we could distribute this, right? We have a term that involves x hat dot y hat, but we know that's 0 because x hat and y hat are perpendicular to each other, and the dot product of two perpendicular vectors always gives us 0. So the only non-zero term comes from this dotted into this, and of course y hat dotted into y hat gives us 1, so we just get an x and a minus 1 from there. So the result is simply minus x. Okay? Well, if we are at the position 1, 1, then x equals 1 at that position. So if I plug in an x equals 1 here, I find that this is minus 1 when we're at that position. Okay? So if I go back to my picture over here, right, I'm at the position 1, 1, which is right here. If I move in the minus y direction, namely like that, first of all, the minus sign tells me that phi is decreasing when I go in that direction, which kind of agrees with my picture, right? Phi equals 1 along this contour line, 0 along the contour line along the x-axis. So phi is definitely decreasing as I move from here to here. That's, again, what the minus sign here tells me. And the 1 tells me that if I move 1 unit in that direction, phi will decrease by 1. Okay? Basically. So it tells me how much my scalar field changes if I move in it in some arbitrary direction. Okay, well, the operator, the differential operator that we used when we wrote down the gradient. Right, we wrote it as this quantity del. This triangle with an arrow over it. You can think of this as x hat times a partial derivative with respect to x plus y hat times a partial derivative with respect to y plus z hat times a partial derivative with respect to z. Think of this as a so-called differential operator. It doesn't really mean anything by itself, but if I write something after it, like the phi, right, then it simply means that we have this quantity right here operating on whatever comes after it, namely the phi, and that means that this derivative will operate on the phi, which of course gives us d phi dx. And similarly, this will operate on the phi, giving us a d phi dy. And similarly with this operator. Okay? So, we'll often write this by itself, but of course it doesn't really mean anything by itself. But it's often useful to just think of this as a differential operator in the sense that it will operate on whatever comes after it, whether that's a phi or some other symbol. So here's a question we can ask then at this point. This is what we get when we have phi operating on a scalar field. So here's the question to ask then. Can this del operator, instead of operating on a scalar field, can it operate on a vector field? Okay, so some vector field V. So remember what that means. V is a vector. Its components, Vx, Vy, and Vz, are each functions of x, y, and z. Okay? So there are two ways that this can work. Okay? The first is the divergence of V, sometimes written as div V, short for divergence, or more commonly written as del dot V. Okay? So this means exactly what you think it would mean if we write out what del stands for. So let's substitute this right here for del. So that's x hat times a partial derivative with respect to x, plus y hat times a partial derivative with respect to y, plus z hat times a partial derivative with respect to z, dotted into v, which if I write in terms of components is vx times x hat plus vy times y hat plus vz times z hat. Okay? And remember, Vx, Vy, and Vz are not necessarily just constants. They are functions of x, y, and z. Right? And each one, right, V sub x depends on x, y, and z, not just x. And Vy depends on x, y, and z, not just y. Vz depends on x, y, and z, not just z. Okay? So anyway, we've got a dot product here. So let's think about what a dot product means. Right? If this were just an ordinary dot product, like A dot B, where A and B are two vectors, I would have A sub x times B sub x plus AY times BY plus AZ times BZ. Right? So let's think about doing a similar thing. The x component there, dotted into the x component there. So now this is not an ordinary vector, it's a differential operator vector, right? So this has to operate on whatever it's going to come together with from this. So when I dot together those two x components there, it's going to give me the derivative of v sub x, partial derivative with respect to x. Of course, this, when I dot it into the y hat or the z hat terms, gives me 0 because x hat is perpendicular to y hat and z hat. So that's all I get from this term. So now this term, again, I could distribute it. I could dot it into this or this or this. When I dot y hat into x hat or z hat, of course, I get 0 because they're perpendicular. The only non-zero one will be this dotted into this. Y hat dot y hat is 1, so this just gives me the partial derivative of v sub y with respect to y. And similarly, from this last term, the only non-zero term comes from that, which will give me the partial of v sub z with respect to z. So, in other words, the divergence of v, this is how to find it, okay? So again, remember these x, y, and z components each can depend on all three variables, x, y, and z, but it's only the derivative of the x component with respect to x, and similarly y with respect to y and z with respect to z, that enters into the divergence. Okay? So this is my expression for the divergence of v. That's what I mean by dotting the del operator into some vector field v. Notice that the result of this is a scalar field, not a vector field. Okay? My result here, vx, vy, and vz are functions of x, y, and z. When I take these derivatives, I can still have something that depends on x, y, and z. But notice there's no unit vectors in the expression here. And so that means whatever I get here at the end is going to be a scalar, not a vector. Okay? Just like the dot product of two vectors gives me a scalar. Right? In a similar way, the divergence of a vector field gives me a scalar field. Okay? And I'll show you an example of that in a moment. But let me show you the other way of doing this first. Okay, so the second way of doing this is to find what's called the curl of V. Sometimes just written as curl V, but more commonly written as del cross V. Okay, this is basically a cross product of the differential operator, del operator right here, and our vector V. Okay, so in other words, the differential operator I'm going to write as x hat times the partial derivative with respect to x, plus y hat times the partial derivative with respect to y, plus z hat times the partial derivative with respect to z. I'm going to cross that into the vector v, which I'll write in terms of components as well. So Vx times x hat plus Vy times y hat plus Vz times z hat. Okay, so you gotta remember how cross products work, right? For cross product, the way to find the x component of the result, in other words, the coefficient of the x hat unit vector, is I take the y component of the vector that's first in my cross product, that's the del vector, so here's its y component, and the z component of the vector that's second in the cross product, namely v. So now, since this is not an ordinary vector though, but a differential operator, that's going to operate on this. So that's going to give us a partial derivative with respect to y of v sub z, and then we'll get another term that involves a partial derivative with respect to z of v sub y. And for the y component of the result, in other words, the coefficient of y hat, I have the z component here and the x component here, so that will be a derivative with respect to z of v sub x minus a derivative with respect to x of v sub z. And for the z component of the result, coefficient of z hat, I take the x component here, operating on the y component there, so that's the derivative with respect to x of v sub y minus the y component there and x component there. So minus the derivative with respect to y of v sub x. Okay, so this is what we mean by the curl, or if you prefer, you can write this as a determinant of a matrix, just like we did with an ordinary cross product. On the matrix, you put the unit vectors x hat, y hat, z hat across the top row. You put the components of the del operator. In other words, the x component is a derivative with respect to x. The y component is a derivative with respect to y. The z component is a derivative with respect to z. Put those across the second row. And then the components of the second vector in the cross product, namely v, across the third row. And now the trick is when you take this determinant. Remember the trick, for example, I multiply those three together, except I don't want to use the word multiply right now. That's a little too simple. What I'm really doing now is letting that operator operate on this. Right? So it's going to take the derivative with respect to y of v sub z. That gives me that term right there. And similarly, this term gives me that term, and this term gives me that term, and then this term gives me this term, or I'm sorry, this term, and so on. This term and that term give me this one and this one. Right? Okay, so let's look at an example. So let's say we have a vector field V that is given by xz times x hat plus y squared z times y hat plus z cubed times z hat. Or in other words, v sub x, which is the coefficient of x hat, is xz. Vy, the coefficient of y hat, is y squared z. And v sub z, the coefficient of z hat, is z cubed. Okay, so let's find the divergence and the curl. The divergence of v, in other words, the derivative of vx with respect to x plus the derivative of vy with respect to y plus the derivative of vz with respect to z. Well, vx, derivative of that with respect to x gives me z. The derivative of vy with respect to y, here's vy, so differentiating that with respect to y, and of course it's a partial derivative, so I just treat z like a constant when I do that. That will give me 2yz. And the derivative of v sub z with respect to z, that'll give me 3z squared. Okay, so that's the divergence of that function. What about the curl? So the curl is once again x hat times the derivative with respect to y of vz minus the derivative of vy with respect to z plus y hat times the derivative with respect to z of vx minus the derivative with respect to x of vz plus z hat times the derivative with respect to x of vy minus the derivative with respect to y of vx. So v sub z does not depend on y. So that derivative is 0. Derivative of v sub y with respect to z, that gives us y squared. Derivative of vx with respect to z gives me x. Derivative of vz with respect to x gives me 0. Vz doesn't depend on x. Derivative of vy with respect to x is 0. Vy doesn't depend on x. Derivative of vx with respect to y is also 0. So, in other words, the curl of v, and just collecting up and simplifying our answer here, we have minus y squared times x hat plus x times y hat. And I guess I should have said, yeah, I mentioned here the result of taking divergence is a scalar field. I guess I should have mentioned here the result of taking the curl, of course, is a vector field. Okay? And you can see that in our example.
I'm sorry, you said divergence is a scalar field and curl is a vector field?
Right.
Okay.
Because you can see right here for the divergence, right, this result is a scalar, not a vector. Right? And you can see the result for our curl is a vector. Right? It's got unit vectors in it. That's the thing that gives it away. Okay, there is one more vector operator I want to show you here. There is also something called the Laplacian. So here's the idea. If we take a scalar field, phi, and we take the gradient of it, and so phi is some scalar field. Well, we already pointed out that the gradient of phi is a vector field. So, in fact, let's for the moment let v represent the gradient of phi. And since the gradient of phi is a vector field, let's just call it v for the moment. So anyway, since the gradient of phi is a vector field, we can take its either curl or divergence. Okay, so again, let's put that in parentheses. Let's let v be equal to the gradient of phi. Let's think what that means then about the components of v. Well, the gradient of phi was, again, the derivative of phi with respect to x times x hat plus the derivative of phi with respect to y times y hat plus the derivative of phi with respect to z times z hat. So v sub x is the coefficient of the x hat, namely d phi dx. And v sub y is the coefficient of the y hat unit vector, in other words, d phi dy. And v sub z is the coefficient of the z hat unit vector, namely d phi dz. So let's now do the divergence of V. Okay? First of all, since V was shorthand notation for the gradient of phi, we could write this as the divergence of the gradient of phi. And now what do we do when we see a vector dotted into itself? If we just have a vector A dotted into itself, we often write that as A squared, right? Because, of course, A is parallel to itself, so the cosine of the angle between them is 1, so the result is just the magnitude of this vector times the magnitude of that vector. In other words, A times A, or A squared. So in a similar way, let's write this, right? Even though del is not an ordinary vector, it's an operator, let's nevertheless write this del dot del thing as del squared. So this is the usual notation for the quantity that I'm deriving here, and this is what I mean by the Laplacian of phi. So the Laplacian of phi, or in other words, del squared phi, is really the divergence of the gradient of phi, or in other words, the divergence of V, if V is defined to be a gradient of phi. Okay? So let's see what that's going to end up being. Okay? So the Laplacian of phi, or in other words, the divergence of V, well, by the definition of divergence, this is the derivative of V sub x with respect to x, plus the derivative of V sub y with respect to y, plus the derivative of V sub z with respect to z. But now, since we know what Vx, Vy, and Vz are from up here, let's plug those back in. So the V sub x was already defined the x, and now we're going to take that and differentiate it with respect to x again. That'll give us a second partial derivative of phi with respect to x. And in this next term, we have the derivative of V sub y with respect to y. Well, V sub y was already d phi dy, so we're taking that and differentiating it the second time with respect to y. That'll give us a second derivative of phi with respect to y. And similarly for the derivative of V sub z with respect to z, well, V sub z is already d phi dz. We differentiate one more time with respect to z. Here is our expression for the Laplacian, okay, of a scalar field. And notice that the result of this is a scalar field. Okay, there's no unit vectors in our result, so it's a scalar, not a vector. And in fact, we know that because it's the divergence of a vector field, and we know that always gives us a scalar field. Okay? So we have four vector operators that we've just defined that are going to appear a lot in what we're going to do for the next few weeks. There is the gradient of a scalar field. There is the divergence of a vector field. There's the curl of a vector field. And now there's a Laplacian of a scalar field. Okay? So we're out of time now, but we're going to, explore more properties of those things starting next time.